Professor Alain Aspect and Professor Yuan Li and Deputy Minister Ye and our faculty students and also our high school students. Good afternoon. It is my great honor to welcome you to National Taiwan University on the public science lecture delivered by Professor Alain Aspect, and also the dialogue between the two Nobel laureates, Professor Alain Aspect and also Professor Yuan Li. Let me first introduce Professor Alain Aspect. He received his doctoral degree from University of Paris-Saclay, and after that, he worked in the French Central for Scientific Research. We always abbreviate as CNIS. Okay? And his very innovative discovery on the entanglement photons makes that, that to prove the field inequality violation and also provide the crucial evidence for non-local behavior of the quantum particles. That's quite amazing and incredible, and also leading the great discovery and advance of quantum information and quantum computing. That's very important for the future technology. And also he co-founded a company called Pascal, and that's very important for the quantum science and technology too. And for the case of Professor Yuan Li, I think everyone knows about Professor Yuan Li. He received the undergraduate degree from my university. And after that, he studied in the National Tsinghua University for the master and also the PhD degree moved from the University of California, Berkeley. And I think everyone knows that he received the Nobel Prize in 1986 on his great discovery on using the spectroscopic technique to investigate the chemical kinetics. And that, I think, that's very important to understand what happens in the chemical reactions. Besides his Nobel Prize achievements, he also devoted very much on science education, and he participated in the international science councils. So he was the president of Academia Sinica and also the president of international science councils. And his leadership makes those two organizations as a great advance at that time. And recently, he devoted a lot of his energy and time in the global challenge, in particular climate change. I think that's a very important issue. We really appreciate for his help. I think that's not only for the Taiwan and for the whole world. And I hope he continue to speak louder than that, and because that's very important for the world. And I think that today is marks very important extraordinary events for the two Nobel laureates to have a public science speech or dialogue. I believe that will inspire our faculty, students, and young scholars to devote their study in the basic science. And I also believe that we will benefit a lot for their speech and dialogues. Finally, I hope to say that actually Professor Aspect just became part of a family member of National Taiwan University, because with honorary doctoral degree yesterday, and also he delivered the Raymond Song speech, chair for leadership speech yesterday, and now both of Nobel laureates are the family of National Taiwan. Anyway, before I close my open remarks, I would like to invite Professor Yuan Li to give his remarks. Thank you. Thank you.
Now, let's welcome academician Yuan Li to extend his remarks for today's event. ladies and gentlemen, because my time is very short, so I have to be very quick. When I was young, not young in 50s, I'm talking about 15s, I read a book written by George Gamow, and the book called Mr. Tompkins in Wonderland. You know that book. One of the chapters was very interesting. Tompkins was talking about, one chapter said, the judgment of photons. In a courtroom, photon was standing in front of the judge, and judge asked him, which door did you come in? There were two doors. And photon said, I came from two doors, both doors. And judge said, how could it be? So the conversation was very interesting, attracted me about science, dualism, and photon, particle nature of photon, and wave nature of photon. And that was a really very exciting book. And when I built the molecular beam machine, especially after I went to University of Chicago, and at the time, I was quite interested in finding the interatomic potential. When two atoms at a distance, it's attractive, and when they come together, it becomes repulsive. And so I used this molecular beam apparatus and tried to see how the atom scatters. And when at the long distance, there's no force, the attractive forces become important. And from this diffraction function, measure the angular distribution, I would like to find the potential. And the first experiment I did know that the neon is a small particle. There's a wave natures. I did expect to see the oscillations. But when I saw the oscillation on the right-hand side, the big oscillations, I was astonished. I didn't know what's going on. Because that oscillation is due to the both Einstein statistics that it has to be symmetric. Only even partial wave contribute. So I did learn something I was not expected. I was very happy. Well, now my 5 minutes is over, so I have to give the speaker to the next speakers. But anyway, thank you very much for having the chance to speak.
Now, ladies and gentlemen, please join me in welcoming today's speaker, Professor Alain Aspect, to deliver his talk titled The Two Quantum Revolutions, From Concept to Applications. 各位贵宾，现在请掌声欢迎今日科普讲座讲者 Professor Alain Aspect.
Okay, I have been advised to try to encourage young people to go to science, and what I will try to share with you is the fact that science is wonderful, either if you want to do basic science or if you want to apply science for nice applications, including applications which are important in the present world. This will be the message I would like to take back home. And in fact, I am going to talk about two quantum revolutions. And in fact, these two quantum revolutions are based on two concepts. The first concept, as mentioned by Professor Lee, is wave-particle duality. The fact that the photon can cut through two doors simultaneously, but also electrons, any particle, can travel in different paths. Wave-particle duality was discovered by Einstein in 1909, and it was generalized to matter by Louis de Broglie, my Frenchman, in 1923. Second concept, at the root of the second quantum revolution, is entanglement. Entanglement, the importance of entanglement was discovered once again by Einstein, but you know he's older here, but here he was really Now it's Einstein a little later. Okay. This is called Larsen effect. I can give you an explanation what is Larsen effect. Okay? No. Okay.
Okay, let me continue. Entanglement. It's Einstein, Podolsky, and Rosen who discovered that entanglement is absolutely amazing, especially when it applies to particles far from each other. I will do my best to explain that. I have to change my pointer. It's really too much amplification. You should lower the level of amplification. Okay. It took another almost 30 years for John Bell to emphasize that entanglement for widely separated particles is absolutely amazing, and this leads to the second quantum revolution. So I will first speak of the first quantum revolution, then on the second, and let us start, of course, with the first one. First, quantization. Why this name quantization? Because at the beginning of the 20th century, physicists discovered that certain quantities which can take any kind of value in the classical world, in fact, in the real world, in the microscopic world, they can take only some specific value. This is the notion of particles. For instance, light, which is classically described as a wave, and you can have any content of energy in a wave, okay? It's a continuous, like a fluid or something like that. In fact, in 1905, Einstein made the hypothesis that light is made of grain of light that we call nowadays photons, okay? But Einstein knew that in the early 19th century, two great physicists, Thomas Young in England and Augustin Fresnel in France, had made experiments and developed a theory showing that light is a wave. Einstein knew that. And so he had to deal with the fact that on one hand, it's a particle, and on the other hand, it's wave. And in 1909, for the first time, somebody made the hypothesis that you can have both wave-like and particle-like aspects in an object, and it was light. Okay. Now, matter. Once again, about matter. Some quantities can take only some particular, we call it discrete values, while the classical formalism allows for a continuum of values. Let us take the case of the atom. This is a Rutherford atom. You have a nucleus, which is positive, and you have electrons, which are negative, orbiting around the nucleus. It's just like satellites around the Earth, or just like planets around the Sun. And it's really like it because the force between the electron and the nucleus goes as the inverse of the square of the distance. So it's really similar. But there is a big difference. Satellite can be at any distance from the nucleus and be on a stable trajectory. But in the case of electrons, to understand the spectrum of light emitted by the atom, Bohr had to make the assumption that only certain trajectories are permitted. Once again, it's not all trajectories, only some of them. This is again quantization. Okay. How to understand that? This was Bohr atom, 1913. To understand it, you have to wait until Louis de Broglie in 1923, because in 1923, Louis de Broglie comes with the hypothesis, which is reciprocal of the one of Einstein, the fact that when you have an electron, we think that an electron is a particle. It is a particle. But you must also associate a wave with the electron. And if you think of the electron on a trajectory around the nucleus, if it is a wave, the wave has to come back in phase, which means that the length of the trajectory has to be an integer numbers of wavelength. With just that idea, evoked by de Broglie in 1923, you understand the condition of quantization of Bohr 10 years earlier. And now you understand this condition of quantization is strongly related to wave-particle duality for the electron. Now, I like these photos. I like these photos because here you have Louis de Broglie, who found that you must associate a wave with wavelength lambda to a particle with momentum p. If you have a wave, you need to have a wave equation. Schrödinger was the one who found the wave equation. 2 years later, de Broglie was 23, Schrödinger was 25. And he wrote the equation. Some of you recognize the equation. The other one are to study it sooner or later if you want to do serious science, okay? Other ones are welcome anyway. I like this photo because look how they are happy. Doing quantum physics is wonderful, okay? I am happy also. Wave-particle duality. With my first PhD student, Philippe Grangier, we demonstrated directly wave-particle duality for a single photon in an experiment that was done in 1986. It was the first time somebody produced well-isolated photon, single photon, in a real scientific meaning. So we are the source here, able to produce single photon. How did we prove that we have a single photon? Because if we send it on a beam splitter, you know what is a beam splitter? A piece of glass, you send a beam on it, and a part of the beam is reflected, and a part of the beam is transmitted. But if you have a single photon, the photon is not partly transmitted or partly reflected. It's either transmitted or reflected, cannot be both. And this is how we demonstrated that we have a single photon. So what you do is you let the photon go and you detect it here, or you detect it here, but you have here an electronic circuit which is called a coincidence circuit, and this coincidence circuit would fire if there was detection on both sides. But in fact, never. The probability to have a joint detection is 0. This proves that you have a particle that goes either on one side or on the other side, but not on both sides simultaneously. Good. Particle-like behavior. Next experiment. Same source, but now we are going to ask the question, do you behave as a wave? And to ask such a question, you must try to observe interference. And there was a reminiscence of that in the presentation of Professor Lee. If I have a wave, the wave will arrive here, and a wave is split in two. And if you recombine it on a mirror, on a beam splitter, on a semi-reflecting mirror, if you recombine, and then you look at the probability to detect here as a function of the difference of path between the two paths here, you observe a modulation of the probability of detection. So you have to understand, it's a single photon. So you send a single photon, you make and you repeat the experiment many times. And sometime, for some path difference, you detect many times here and never here. Then you slightly change and you detect many times here and not at all here. And the modulation proves that it is a wave which is split into parts and recombined. So this time we have a particle-like behavior. But look, it's the same source, the same single photon pulses. We don't change anything in the source. The first experiment shows that it is like a particle going on one side or the other one. And the second experiment shows that it is like a wave being split in two and recombined. This is wave-particle duality. Now, when Einstein was telling Bohr, this is crazy, cannot be like that, Bohr would say, look, in fact, it's not so surprising. I think it is surprising, but Bohr say, it is not so surprising Because you have to choose. Either you use this apparatus, and this apparatus is meant to ask the question, are you a particle? And then it answers, yes, I am a particle. And this apparatus is meant to ask the question, are you a wave? And the answer is, yes, I am a wave. But you cannot ask the two questions simultaneously. You have to choose between the two questions. That's the philosophy of Bohr. Okay. First quantum revolution. First quantum revolution is based on this concept. This concept of wave-particle duality and Schrödinger equation was first used to understand many physics properties that physicists could not understand at the end of the 19th century. Stability of matter. Why am I here? Why is this table solid? Because of quantum mechanics. And I elaborate that. Matter is made of charges, positive and negative. Okay, they knew that at the end of the 19th century. And positive and negative charges attract each other. So if matter is made of charges, positive and negative, and they attract each other, matter should collapse. You should collapse, this should collapse, we should all collapse. Why don't we collapse? Because of quantum mechanics. It's because of the wave nature of the electron that the electron cannot crash on the nucleus like a satellite eventually crash on Earth. It is the wave nature of the electron which prevents the electron to eventually crash on the nucleus. So the mechanical properties of matter, the electrical properties of matter, the optical properties of matter are all understandable by using quantum physics. So it was first a scientific revolution, thanks to wave-particle duality. You can also understand some strange properties like superconductivity, superfluidity. You have heard this name, but I will not elaborate. This is just an example of the use of superconductivity. Wave-particle duality did not lead only to scientific advances. It also led to wonderful technological applications which have changed the society. Young people, you don't realize that when I was young, and even when I was 40, there was no internet, there was no computer. All this has been allowed by the wave-particle of duality. What do I mean? Transistor. First transistor was invented in 1947, the year when I was born. Thank you. It's my... So you see, it took more than 20 years between the establishment of the right equation, Schrödinger equation, for describing the motion of electron, and the moment when physicists and engineers were able to use their understanding of how an electron propagates in matter using the equation of quantum mechanics, and then doing a lot of engineering work to purify material, etc. And eventually, you have the first transistor, 1947. Another 1 or 2 decades, I think, and you have integrated circuit. Integrated circuit is many transistors on the same chip. And it is your computer, your smartphone, etc. Laser. Laser was invented in 1960. Do you know when the equations that we still use to describe a laser were found and were written? They were written in 1916, 16. By whom? By whom? Einstein again. Einstein wrote in 1916 the equation allowing one to understand, or to describe, I should rather say, how light is absorbed or emitted by matter. And these, I teach a course on lasers, and these equations are still equations that we are using to describe a laser. So it took from 1916 to 1960 to put this equation to use and invent the laser. And these inventions of laser of transistor and integrated circuit were not done by a guy knowing almost nothing and working in a garage, okay? It was done by the best scientists of the time. They got Nobel Prizes for inventing these things by use of quantum mechanics. And now we have the information and communication society, permitted by laser, transistor, and integrated circuits. So the first quantum revolution was conceptual, wave-particle duality, scientific, structure of matter, technological, laser, and transistor. Okay. Now, I'm going to speak of the second quantum revolution, and I will follow the same path. First, the concept, then scientific applications, and hopefully technological applications. Entanglement. I will describe it using photons. Now, I don't speak of one photon, I speak of two photons. I have a photon going to the left, a photon going to the right. Okay. On these photons, I'm going to make polarization measurement. What does it mean? When you quantize something, you must remember of the wave properties. And so a photon is nothing else than quantizing electromagnetic wave. And an electromagnetic wave propagating like that, in fact, is made by an electric field oscillating perpendicular to the direction of propagation, which means that you have a vector called the electric field, which can have any direction in a plane perpendicular to the direction of propagation, which means that this electric field lives in a two-dimensional space. So it can have two components. Okay, so a polarizer is an apparatus that can tell you what is the polarization of your wave. If you set the polarizer with a vertical axis, and if light is polarized along that axis, then the beam will go up. That is plus one channel. If light is polarized perpendicular to the axis of the polarizer, then light will go down, minus channel. And if light is polarized at an angle, a fraction of the beam will go up and a fraction will go down. But if we have a single photon, it's again the same story. The single photon will not be partly up and partly down. Sometimes it will go up, sometimes it will go down. This is quantum physics. Quantum physics allows you to calculate probabilities. So if you know the state of the light, you can tell if it goes, what is the probability to go up and the probability to go back. And so the big discovery of Einstein, Podolsky, and Rosen is the fact that if you think of a quantum state of that kind, then it becomes very interesting, and I'm going to spend 2 minutes to tell you that. This is a wonderful notation by Dirac. Dirac was an absolute genius, including for the fact that he gave us extremely simple notation. You have an example here. This is a state describing the two photons. It's composed of two components. The first component corresponds to a pair of photons with both photons polarized along x. It's simple. You cannot think of a simpler notation. Second term is a pair of photons composed of two photons polarized along y. The big discovery of Einstein, Podolsky, and Rosen is that if this is a state which is allowed, and if that is a state which is allowed, then the superposition of the two is also a state which is allowed. And this is very surprising. Why is it surprising? Because those of you who know enough of mathematics, you can easily demonstrate that this cannot be factorized in a component for the first photon and a component for the second photon. If you could factorize it, you could say, oh, the first photon is like that and the other like that. But you cannot do that. It's impossible to factorize that, which means that the pair of photons is simultaneously XX and YY. And there is no other way to say it. It's both. That's the property of entanglement. And with a little bit of exaggeration, this is as surprising as the Schrödinger cat, which is both dead and alive. Of course, Schrödinger cat is more than two particles. This is why I say a little bit of exaggeration, but it's similar in nature. Having a Schrödinger cat, both dead and alive, would be, in a sense, like the pair of photons being both this and that. Okay. Once you know the state, the mathematics of quantum mechanics is quite easy, and you can calculate the various probabilities to find result +1, result -1 when the polarizer is in orientation A, etc. And when you do the calculation, you find that the probability of going up or down is the same, 1/2, 50%. So the photon arrives here, 50% chance to go up, 50% chance to go down. Same for the other one, whatever the orientation. But now comes the interesting part. If the two polarizers have the same orientation, and if you compare the result on the left and on the right, that is to say, looking at correlation, you find a remarkable fact. If you get +1 on the left, you get +1 on the right. If you get -1 on the left, you get -1 on the right. You never get +1, -1. We say that this is a random variable, this is a random variable, but these two random variables are totally correlated. The outcomes are the same. This is what I call a tricky coin toss. What do I mean? You have a guy over there throwing a coin. Another one here throwing a coin. People over there look at the guy and say, well, it looks really random. Eh? Sometimes it's head, sometimes it's tail. People here look and say, well, it looks totally random. Huh? Sometimes it's up, sometimes it's down, etc. But people in the middle, observing carefully, observe something strange. If it is head here, it's head here, and if it is tails here, it's tails here. There is a trick. If you see two people doing that, you see there is a trick. And you want to understand the trick. I am a physicist. I want to understand the trick played by the photon to give this tricky result. That's the goal of physics. The goal of physics is to observe things which are surprising, amazing, and to say, I'm going to find an explanation for that. Okay. Here, of course, you can say, but we have already the explanation because we have done the calculation. The calculation is the explanation. So let us look at the calculation. And can we make an image, a description in our space here? Can we make a description in our space of what happens? And the answer is, by looking at the calculation, the answer is no. Why? Because the calculation is done in an abstract space that we call a Hilbert space, which is a space where you describe simultaneously the two photons. So it's a complicated mathematical space. And you do the calculation in that space, and you get the result. But I don't know how to make an image in our space just for this calculation, which is done in the abstract space. And the red thread is the fact that one cannot identify individual properties for each photon because we cannot factorize the state. I already told you. But there is a famous quantum optics book in which the writer, which is totally orthodox, makes this strong sentence: quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. My experiment was done in a real laboratory. I had a source here, a detector here, a detector on the other side. I want to understand what happens in my laboratory, not in an abstract mathematical space. Okay. And so I demand an interpretation in real space. And then at this point, we have the reasoning of Einstein and his colleagues. Einstein say, look, if the two particles are distant, and if you have a strong correlation, there is a very simple and natural interpretation consists of saying that from the beginning, the two particles have some joint property, and this joint property will determine the outcome. For instance, from the beginning, both photons are polarized along x, and so no surprise that you get +1, +1. Maybe next pair, both photons are horizontally polarized, and then no surprise, you get -1. And so you develop this idea, and why was Einstein happy with this idea? Is because Einstein thought that a fundamental theory cannot be probabilistic. Einstein had no problem with probabilities. You should know that in 1905, he wrote a wonderful paper about Brownian motion. And this wonderful paper is based on sophisticated probabilities. So Einstein had no problem in using probability. But he thought that a fundamental theory cannot rely on probability. Probability is good for a theory which is a kind of statistical physics, but there should be an underlying level. And so Einstein thought that the world was like that. But here, he thinks that he has demonstrated that you need to introduce this underlying level, otherwise this tricky coin game, you cannot understand it. If you want to understand it, you have to imagine that somebody is taking two coins, give the two coins of the guy, and from the beginning, the two coins are head. So no surprise if they throw it that you have head, okay, head, etc. So the idea was the only reasonable image is an image in which you introduce supplementary parameters. Note that this image is extremely reasonable. It's absolutely scientific. Our colleagues in biology or medical doctors, for a long time, even when they have not yet been able to decipher the genetic code, they had already understood that when you have twin brothers or twin sisters, they had understood that the joint properties, same color of eyes, same disease, were due to joint chromosome, to the similarity of the chromosome. This is exactly the same idea. You have the same property lambda for the photon on the left and photon on the right. So this is what we call supplementary parameter or hidden variable. Okay, Bohr did not agree. Bohr had a strong intuition that if you allow this, if you try to complete quantum mechanics this way, something will be wrong. But I am sorry to say that Bohr did not demonstrate that. He had a lot of argument, philosophical argument, saying, but you are talking of an experiment you could do, but you do not do it, etc. It was philosophy. It's okay to do philosophy, but philosophy is not science. And so I am sorry to say that the reply of Bohr is convincing only people who already have adopted the philosophy of Bohr. If you have not adopted the philosophy of Bohr, if you are a follower of the philosophy of Einstein, there is no reason to be convinced by the reasoning of Bohr. So what happened? Nothing. Nothing. Nobody cared. Most of the young physicists, you know, young people do not listen to old people, so you should not listen to me. Young people were working in the lab, working with the formalism of quantum mechanics and describing all the phenomena they had in the lab. So quantum mechanics was obviously very successful. And somebody told them, you know, there is a discussion about Einstein and Bohr about the interpretation of the quantum formalism. Bohr say, you only have the formalism, and Einstein say, you must complete it. But they all agreed on the way of doing the calculation. They all agreed on the way to calculate the outcome of an experiment. So you are working, somebody says there is a discussion, but the discussion is only about interpretation. You have no time to waste. You go to the lab, do an experiment, calculate, and it works, period. And for this reason, nobody cared, really, until the death of Einstein and of Bohr. Well, a small number of people, but almost nobody cared. Okay. 2 years after the death of Bohr, John Bell, a theorist at Geneva, you know CERN, the big accelerator in Geneva, where they discover elementary particles, etc. He was a theorist there, using everyday quantum mechanics to calculate the properties of particles. But he was worried by the equation of interpretation. And he looked again into the reasoning of Einstein, and looking into the reasoning of Einstein, he discovered an amazing property. If you take seriously the point of view of Einstein, if you develop any kind of what I will explain, local supplementary parameter theory, that is to say a theory in the spirit of the chromosome and something like that, you arrive at a conclusion which is in contradiction with some quantum mechanical calculation. And so now you no longer have only a question of interpretation of philosophical debate. You can settle the debate between Einstein and Bohr by doing an experiment. This is amazing, isn't it? A philosophical debate can be settled by doing an experiment. You do the experiment in a situation where Bell shows that there is a contradiction between the point of view of Einstein and the point of view of standard quantum mechanics. You do an experiment in such a situation, and either you find quantum mechanics and Einstein is wrong, or Einstein is right and you have found a place where quantum mechanics is wrong. So you are going to tell me, well, it's impossible that quantum mechanics is wrong. Come on. All physics theory, sooner or later, finds its limit. It does not become wrong. It remains right in all the phenomena that you have already investigated. But everybody believes that sooner or later you will find some specific situation where you are going to find that the theory is wrong. So it was interesting to do the experiment. First generation of experiment done by John Clauser in Berkeley, Pipkin in Harvard. It was in 1972, and believe it or not, they found opposite result. Clauser was in agreement with quantum physics, and Pipkin was in agreement with Einstein's point of view. So there was a debate, but there were more experiments. Another one by Clauser, one by Fry was working in Texas, and after a few years, the score was 3 experiments in favor of quantum mechanics, 1 experiment in favor of Einstein. Okay. This is John Clauser. John Clauser received the Nobel Prize 2022. Okay, we received this simultaneously. So John Clauser in 1972 had found the result which was supported by latest experiment. Okay. So this experiment was fantastic. It was a pioneering experiment, but it was far from the ideal scheme that I described. If I would go into detail, you would see that it is really not exactly the experiment that I have described. So in 1974, I read the paper by Bell, and I decided to embark into a new series of experiments for going closer and closer to the ideal scheme that the theorists were discussing. So this was my experiment developed in Institut Optique between 1975 and 1982. The final results came in 1982. The major advance was building a source of entangled photon much better than the previous one. Professor Lee knows, he is an experimentalist. If you improve the signal, life is nice, right? Okay. So my source of entangled photon was orders of magnitude better than the previous one. I could do a significant measurement with 1% accuracy in 2 minutes. It took hours to Clauser to have only 1 point. It took me only 2 minutes to have 1 point. And so with this, I could develop scheme. This was the first scheme which was totally different from the previous one, and now you have a scheme that resembles the one that I have projected. You have the +1 channel here, the -1 channel here, coincident circuits, etc. It really resembles the ideal scheme. We did that experiment we found a violation of Bell's inequality, that is confirmation of quantum mechanics, by 40 standard deviation, 40. You must know that, again in Geneva, they have a background, and there is a bump above the background. If the distance between the bump and the background is 3 standard deviation, they leak the information to journalists that maybe they have discovered a new particle. And it takes 5 standard deviation to be allowed, or to, that's the tradition in physics, to publish, we have discovered something. Here it's not 5 standard deviation, it's 40 standard deviation, so it's no discussion. Last experiment, the one which granted me the Nobel Prize. John Bell has suggested, in the conclusion of his paper of 1964, he had suggested to have the full conflict between Einstein and quantum mechanics. You should be able to change the orientation of the polarizer at the very last moment when the photon arrives on it. Should not be set in advance. You should change the orientation at the very last moment. It was difficult to change the orientation of my polarizer, which was a heavy object, but what I found is a possibility to use a switch, able either to let light go straight or to deflect light towards another direction. You put a first polarizer in orientation A, a second polarizer in orientation A prime, and if the switch is fast enough, then you have equivalent of a single polarizer going from A to A prime, back to A, back to A prime. This is what I could do, and I could demonstrate it without what is called quantum non-locality. That is to say, the fact that until the last moment, it can still be +1 or -1. And it is only at the last moment that the decision is made. But when the decision is made on one side, instantaneously you have the similar result on the other side. This is quantum non-locality. It's crazy. It's totally opposed to all the ideas that we have, but that's a fact. We have to accept the result of experiments. This is called quantum non-locality. Third generation of experiment. My experiment was 82. Starting in the late 80s and more in the 90s, okay, they developed new source yet better than mine, okay? My source was order of magnitude better than the one of Clauser, and they developed source much better than my source. They were much better in the following sense. First, a lot of pairs of photons emitted, but I also was able to emit many photons. But the important point is that it was produced by a crystal, a nonlinear crystal, and one of the properties of nonlinear phenomena, optical phenomena in a crystal, is what is called phase matching. It is a fact that when you take an ultraviolet photon, you split it in two by so-called parametric down conversion. So now you have your two entangled photons, but these two entangled photons are emitted in extremely well-defined direction. So well-defined that you can inject them into optical fibers. And then you can stretch optical fibers over hundreds of meters. This is the experiment that Zeilinger did in 1998. He replicated my experiment, but in a more sophisticated way. That is to say, the photon was emitted, and while the photon was traveling in the optical fiber, he could launch a random number generator to decide randomly of the direction of the polarizer. In my experiment, it was not random. I was switching from A to A prime back to A. Zeilinger did it with a real random, but it was 98, okay, 16 years later. So after 16 years, you should be able to improve the experiments, okay? Nicolas Gisin in Geneva has demonstrated that he can use a commercial network of telecommunication, optical fibers telecommunication network in Switzerland. He introduces the entangled photon here in the center of Geneva, in Cornavin, and makes measurement in two villages which are at several kilometers from the injection, entanglement is still there. There is still violation of Bell's inequality. Okay. Many more experiments, okay, so this one was 98, and many more experiments until in 2015, people claim test of Bell's inequality without any possibility of a loophole, which is okay. And there have been experiments at 30 kilometers. Giant Weapon in mainland China has done an experiment from a satellite showing entanglement at more than 1,000 kilometers, sends the 2 photons from a satellite and observe entanglement. There is no doubt. Einstein's point of view must be abandoned. What is Einstein's point of view? It's called local realism, and I will explain what it is. What is the conclusion of the fact that we must reject Einstein's point of view? Well, in fact, we can read it in Einstein's paper. Einstein says that he was wrong. No, he was not saying that he was wrong. He said, if I was not right, this is what you would have to accept. Reasoning ad absurdum. But we know that he is not right. On this, he's right in so many things, we can forgive him, okay? But on this, he is not right. And so, he told us what we have to swallow. He thought that it was impossible to swallow. We have to swallow it. Okay. So these are the words of Einstein. If he was not right, if you could not explain the correlation by joint property going with the particles, then you would have to accept one of two things. The first one is abandon the independence of the physical reality present in distant volumes. This is local realism. It's the fact that we have two objects, and these two objects are separate. There is a duck somewhere, no? It was a strange noise. Quack, quack. You have two objects separated. And the idea of local realism is the fact that you can speak of the properties of this system. This property will determine the result of any measurement you do on it. It's called the local reality, the reality of the system. And it's local. It's associated to the volume in which you have the system. And you have the other system here, and you have the properties, and this property determines the result. And once you know all these properties, you know the result of any measurement. Well, we have to abandon the idea that the system is fully described by all the properties of the first one and all the properties of the second one. There is more in the global system than in the addition of the property of the first one and the second one. This is called quantum holism. And it's very important for application. I will tell you a few words about that. The other point of view, still Einstein says, if I was not right, you would have either to abandon the independence of the physical reality, local realism, or accept that the measurement on the first system instantaneously plays a role on the other system. This is called quantum non-locality. Quantum holism is the concept at the root of quantum calculation. It's the fact that when you have an entangled object, the amount of information that you can store into that object, this ensemble of entangled objects, is huge. It increases exponentially with the number of objects. So when you have 2 is not so much, but 3 is 2 times more, 4 is 2 times more, etc., etc. And when you have 100, you have billions of bits of classical energy in it, information in it. So the quantum holism is the idea, the concept at the root of quantum calculation. And quantum non-locality is at the root of quantum communication. Okay. Now, I have a kind of a demonstration. I will skip the beginning of the demonstration. This is a calculation which is based on standard quantum mechanics, but now I make the hypothesis that there is first a measurement here and then a measurement there. And this will allow me to build an image. You know, I want to have an image in my space, okay? And this will allow me to build an image in my space. So I have my first photon going here, and then a measurement on the first photon. And the second one is a little later, okay? Now here, as I already explained, I can have either +1 or -1. What happens there? I go to the standard books of quantum mechanics. It's totally standard quantum mechanical calculation. And they tell me that just after the measurement, I must project onto a mathematical space which is associated with the result. In other words, if I find the result +1, associated polarization X, the projection of the initial state onto the state associated with the result gives XX. Which means that now, until the last moment, it could be either X or Y. But if I find X, then instantaneously the second photon is X. And if I find Y, instantaneously the second photon is Y. This is quantum non-locality. That's the image that I have of quantum non-locality. Okay, and with this you can discuss and discuss and discuss, okay? And it allows you to explain the total correlation at a distance. So you have an image in real space which yields the same result as the calculation in the abstract Hilbert space tensor product of the spaces of the two. But this image is quite strange and of course not palatable for Einstein. Until the moment on the measurement on U1, you can get +1 or -1. But immediately after the measurement, the polarization of the other one is exactly the same as the one that you have found. And don't tell me that from the beginning they're the same, because violation of Bell's inequality precisely tells you that this does not work to describe it by an initial joint property. That's quantum non-locality. Okay, so what do we do with that? Well, quantum mechanics, quantum non-locality can be used, and I will give you only one example. I have to tell you that many physicists do not accept what I am telling you. They say, come on, this non-locality is because you insist on having images. But we do not need images. We can just do the calculation and compare to the result in the laboratory. This is called shut up and calculate. That's the most frequent school among physicists. They say, no need to ask questions to try to make images, shut up and calculate. I am somebody who calculates, but before doing calculations, I like to have images. And non-locality gives me fruitful images. And I give you an example. Quantum cryptography with entangled photon. First, classical cryptography. Robert Shannon, the inventor of the theory of information around World War II, before and after, demonstrated that there is a totally sure method for communication between two friends, Alice and Bob. This method, so they want to communicate and they don't want the spy, which is called the eavesdropper, somebody who listens, okay? They don't want to have the eavesdropper understanding the message that they have, okay? And there is an absolutely safe method, which was once again discovered and demonstrated on the basis of mathematical demonstration, absolutely rigorous by Robert Shannon. It is just using a random series of 1 and 0 to encode the message, and the same random series of 1 and 0 to decode. And you can easily understand, because if you do a Boolean addition, 1 plus 1 equals 0. So let's suppose you start with a 1. You start with a 1 from Alice, and then you add a 1, you get 0. And when Bob adds a 1, he gets 1 again. So the initial 1 is understood as a 1, etc., etc. But what Shannon demonstrated is that the message must not be longer than the random series of 1 and 0. And the reason is that if the message is longer, you reuse the same encoding key several times. And mathematicians who try to decode message are extremely smart, and they can notice regularity. And if they notice regularity, at the end, they become able to decipher the message. So the problem boils down to how do we do to distribute to Alice and Bob two identical series of two numbers, okay, without the spy having a third copy? The answer is quantum. Quantum K distribution based on entangled photon. Look, here I have one of the modern sources, okay, not my source, but the modern source of entangled photon. One goes to the left, one goes to the right. Alice makes measurement either in direction A or in direction A prime. Bob makes a measurement either in B or in B prime. Okay, they have decided that in advance, and they choose randomly. When it is finished, they communicate by radio, open radio. The spy can listen to the radio, doesn't change anything. And Alice say, okay, first case was A, second case was A, third case was A prime. And then Bob say, oh, first case, I had B equal to your A, so we can take the result. Why can't we take the result? You remember, it could be +1 or -1, but if it is +1 on one side, it's +1 on the other side. So after a while, they know what are the cases that they should keep and what are the cases they should eliminate. And with that, they have a long series of random numbers that they can use for encoding K and decoding K. Good. Where is non-locality? Why is non-locality useful? Well, for an obvious reason. If the spy, the eavesdropper, tries to intercept things here, there is nothing to spy because of non-locality. Because of non-locality, until the last moment, you don't know if it will be +1 or -1. So there is nothing to spy here. This is the root, the basis for the success of this method of quantum cryptography, which was invented by Arthur Eckert. It's because nothing is decided until the last moment that there is nothing to spy. If the eavesdropper is smart enough to make a measurement and resend the photon with the same polarization that he found, you can easily demonstrate that then Bell's inequality are not going to be violated. So with the remaining results, the result at which the angles are different, Alice and Bob can make a test of Bell's inequality. If they violate Bell's inequality, it means that the spy is not doing that maneuver. If they don't violate Bell's inequality, they say, we better not use our results. And once again, at this stage, you are not sending the information. At this stage, you are preparing the key for encoding and decoding. And so this is the idea. So it's probably written here, there is nothing to spy during the propagation of the photon. The key are created at the moment of the measurement because of non-locality. Okay. Once again, Jian Weipan has established a satellite sending entangled photon and demonstrated quantum cryptography at more than 1,000 kilometers. Okay. So, do we have a second quantum revolution? Well, first, I want to emphasize a point which was implicit in the discussion, but now it will be made explicit. The second quantum revolution is based on entanglement, but it is based on something else, which is the manipulation of individual quantum objects. Until 1970, I'm sure you remember, all physicists thought that quantum mechanics was only about large ensemble of objects. You say, I have a vapor, many atoms, I send light on the atoms, I observe fluorescent light, and you calculate it as the result of many, many interactions with the atoms. Starting in 1970, Hans Dehmelt was able to trap a single electron. Trap it, observe it, manipulate it in a sense, okay? Don Eigler in IBM was able to manipulate single atoms on the surface of a crystal. We were able to produce single pairs of photons. What do I mean by single pairs? In order to measure the correlation, I must measure it on a pair of photons. The first pair of photons must be distinguished from the other one, from the either one. If I look at the correlation between a photon of one pair with another pair, there is nothing. So in order to do the kind of experiment that Clauser did and that I did, you need to be able to identify individual pairs of photons. So you see, all this idea of having individual quantum objects is deeply in the second quantum revolution. So there are many efforts, other single photon, Serge Haroche in France, here manipulating single atoms, etc., and big deal, people trying to observe and manipulate individual silicium atoms, and so if they succeed with that, they have all the technology of semiconductors, which is quite famous in this country, okay? So people are doing a lot of efforts to develop entanglement between individual defects on silicon, okay, or other semiconductors. There are also people working with quantum circuits which behave as single quantum objects. And all this is all this work of people trying to develop better and better quantum bits. A quantum bit is nothing else than an individual quantum object that you can manipulate at will and entangle at will. And so I come to the end. What I want to show is that if we have a revolution, a second quantum revolution, well, we already have a conceptual revolution. Understanding that entanglement is really something extraordinary, non-locality, holism, etc., is a conceptual revolution. It is also a scientific revolution because already physicists use the notion of entanglement to understand plenty of properties in solids, etc. The question is, what about applications? Well, we have three fields for application. Quantum communication, I already mentioned cryptography. There is also teleportation. Teleportation is not Star Trek, okay? It's not teleporting me to a planet or a galaxy or something like that. Teleportation is taking the quantum state of a system here and bringing it there. And this will be extremely important when we have, if we have quantum computer, because the output of a quantum computer can be fed into a second quantum computer, directly transporting quantum information, teleporting quantum information. You could not do it by making a measurement, because when you make a measurement, you destroy a part of the quantum information. So the idea is to be able to transport the quantum information from here to there without destroying it on the way. So that's quantum teleportation. I can tell you, it's as surprising as teleporting me to the galaxy Andromeda. Quantum computing, to make a long story short, there are two branches: imperfect quantum computing and perfect quantum computing. Imperfect already works. We are at the stage where the imperfect quantum computers can already solve problems difficult to solve with a classical computer. But the dream is to make ideal quantum computers, that is to say quantum computer where you have error correction. Because we always have imperfect bits. And when you have imperfect bits, the idea is to use redundancy to encode the information on more than one qubit. This is already at work in classical informatics, okay? In classical informatics, we have also errors, but you encode the information on 3 bits rather than 1. And if you encode on 3 bits rather than 1, if there is one error from time to time, that's okay because you have 2 bits left with the right information. Here it's the same idea, except that the overhead is much bigger. The overhead is 1,000 quantum bits to have one ideal error-corrected bits. So the price is very heavy. So we have to do something. Nobody is able to have 100,000 quantum bits of best quality to make an ideal. So there are two ways to do that. First way is to improve and improve and improve and have 100,000 qubits better and well entangled. The other way is to have mathematicians smart enough to demonstrate or to invent error correction codes where the price is not as high. There is no reason why it should be 1,000 qubits. There should be error correction codes which are much more friendly, okay? And maybe with only 100, maybe 50 quantum bits, you could have one ideal qubit. And this is a path towards ideal quantum computer. It does not work yet. Finally, quantum metrology. This works. This is a cold atom interferometer which is sold by a company which was founded by some of my former students. It works so well that it works 24 hours a day, 7 days a week, 360 days per year, okay, on the slopes of several volcanoes in the world. The hope is that by observing fluctuation of gravity, you may anticipate volcanic eruptions. No need to tell you in this country that if you can anticipate big earthquake, that's very important for the society, okay? So there is hope that this can be useful. You have quantum sensors based on so-called NV centers. Thierry, who is here, is developing this kind of sensors. Jean-François, who is somewhere around, je ne sais pas où il est, Jean-François, over here, is also using such quantum sensors. This also works, okay? And so there are some quantum technology which already work. Now, it has to be clear. It's not broad market application. It's niche application. And so, does it change the society? Will it change the society? We don't know. It will change the society if these applications become large market application and not only niche application. So, will the new quantum revolution transform our society? I don't know, but I want to make a final comment, especially addressing young people. You may hear about the quantum advantage. A quantum computer could have a quantum advantage, that is to say, be better than a classical computer. The point of view that you usually listen to is, oh, a quantum computer could do calculation so complicated that a classical computer cannot do it. Yes, this would be a quantum advantage. But there is another point of view. The quantum computer could do the same calculation, but using much less electricity. And this is a big issue. You young people are concerned by the planet, by not using too much energy, etc. It may be that the quantum advantage is saving energy compared to classical computing rather than doing more complicated calculation. And so I think that you should really think in this sense. So what I show here is that there are all states here, it's in France, but all states in the world develop quantum programs. Companies which are rich spend a lot of money in trying to develop quantum computers and quantum technologies. And recently I visited Foxconn here, and they also have a quantum computing branch. There is a computing effort in Italy, and many startups. I am a co-founder of this one. I am in a scientific board of that one. This one is about neutral atoms used as qubits. This one is about photon used as qubits. We have also this one. Well, all these are French startups, but there are startups everywhere in the world, including, of course, in this country. And, okay, plenty of startups, fascinating perspectives. And Just to finish, I want to say that to do these experiments, I was helped by two wonderful engineers, one in optics and one in electronics. And at the end, at the very end, I had two master students. And I like to cite them because these two master students, really beginner, they were fantastic in the lab. I was so happy to work with them. And it was a good start because these two people have become people who know the domain, have become really stars of quantum physics in the modern world. They are known everywhere, Jean Dalibard and Philippe Grangier. And you know, I was really lucky to have these two students when started, and as a reward, I invited them to come with me to Stockholm. So this is me with Jean Dalibard and Philippe Grangier, ready to go and collect the medal from the King of Sweden. Thank you very much.
Ladies and gentlemen, it is now time for the joint forum session, where we have the incredible honor of hosting two Nobel laureates, Professor Aspect and academician Li. The session will be moderated by Professor Qiaoxuan Wang. Now, please join me in welcoming our distinguished guests to the stage.
Good afternoon, everyone. Thank you all for joining us today. I'm Qiaoxuan Wang, an assistant professor of physics at National Taiwan University. I'm also one of the people happily studying quantum mechanics like Professor Aspect. It is a great honor to moderate this joint forum featuring our two distinguished Nobel laureates, Professor Aspect and Professor Li. So before we start this forum, I'd like to outline how this forum will proceed. We will start with 4 pre-collected questions for both of our laureates, which will cover important themes, including scientific innovations, interdisciplinary collaborations, and the role of science in society. Afterward, the floor will open for live questions. And I encourage everyone to make the most of this valuable opportunity by reflecting on any questions you may have for our laureates. And when constructing your questions, please make sure they are concise, focused, and in English. Okay, so let us get started.
Or in French.
Or in French. Okay, let's get started with our first question for both of our laureates. So to begin, many students, they are eager to understand what the differences of research in academia and in industry. For example, universities have been the centers for fundamental discoveries, while big companies like Google and IBM, they are currently at the forefront of quantum technologies. So we would like to know, in your view, do universities still hold their unique advantages compared to industry labs? And how do you see these differences could impact future innovations in physics and in chemistry? So, Professor Aspect, would you like to start by sharing your thoughts?
Okay, I will start with an example. I've shown this apparatus for measuring gravity. First experiments were done in the lab. And in the lab, it was a proof of principle. They demonstrated that they can measure gravity with a high accuracy. But it was a lab experiment. It demands experts, it demands postdocs, professors, graduate students, etc. And then they decided to make a startup. Well, I was involved in that company also, because all these people are my former students, okay? So they came to me and said, well, this is an interesting story. What do you think of our idea? I said, it's a good idea. Do you support us? Yes. Do you support us? Yes. At the third time, I understand what they mean by supporting is giving them some money. Okay? So I supported them. It took several years to transform the experiment of lab into a push-button experiment that you can put on the flame of on the side of a volcano and have it running all time. Okay. This is industrial research. Industrial research is transforming a proof of principle into an apparatus that you can deliver to people who are not expert and who can use them. And this is extremely interesting because to improve or to make the apparatus reliable is not just a small thing like that. It's understanding in detail what is the reason why your apparatus is not totally reliable, understanding basic physics of what is the reason for this fluctuation that you want to fight, okay? And this is very interesting, but it takes years. It took them years to have a laser which was immediately going at the right position to excite the atoms, okay? And there is a reciprocal benefit, because when a society, when a company develops a laser like that, it can sell back such lasers to academic researchers, and the academic research can use their time in doing something else than tuning their lasers. So there is a very nice process in that. And so, in general, this is a difference in basic research, which is going to basic principle, proof of principle, and applied research, which is transforming it into reliable thing. Now, the case of Google, etc., is a little special, because they have so much money, they can do both. They can be on the forefront of the basic research and also on the industrial research. But it's not clear, because, you know, they depend on the stock market. And as soon as the stock market changes, then they may immediately cut the basic research. So if you are invited to go to do basic research with these big companies, know that there is a risk that at one moment, when it works, you have plenty of money, it's efficient. But you should know that at one moment, if the stock value decreases, then they may stop the basic research. In university, we don't have as much money, but we have long term. Both approaches are very interesting. You have to choose, or at least you have to be aware of the difference. I'm talking to all these young people. Older ones know.
Thank you, Professor Aspect, for sharing your story.
Professor Lee wants to comment. No?
So, yeah. Professor Lee, could you share your thoughts on the differences between industrial and academic research?
I just want to apologize that the academic organization, like National Town University, is a slave driver. Keep on driving you without giving you 5 minutes break. So I apologize.
Thank you very much. They will have to pay for that. A good dinner.
There's a main difference between academic research and industrial research. Academic research, we will keep on going and trying to find the truth. But industrial research, want to see the return in 5 years. And that's a major difference. So when you ask someone like Maurice Sang to invest in the research, he would ask how many years will we see the return. If he said more than 5 years, shake his head, and that's the difference between industrial research.
And my bet is that universal quantum computer will take more than 5 years.
So thank you for sharing your stories and insights. And I think it's you're highlighting these different roles that universities and industry play in driving innovations. They have complement each other in different ways.
Yes.
And I think it's also like important some guidance for students that you have to think about what are the differences and which fits your lifestyle and philosophy better. Okay, so thank you. Let's move on to the second question, and that's regarding the role of AI in science. So we all know that artificial intelligence has played a growing role in many research areas. And especially this year, the Nobel Prizes in Physics and Chemistry were awarded for AI-related work. So we are wondering how you see AI shaping the future of the fields And do you think they would change the way that we approach fundamental science? So for this question, Professor Lee, would you like to start by sharing your thoughts?
Well, artificial intelligence certainly will influence the research we are carrying out now. Because when we are doing research, we collect lots of information and then try to understand what's possible, what is possible with artificial intelligence. Certainly, it will help you. But one thing we always ask is when say intelligence, then the other one is stupidity. So if I want to answer artificial intelligence, I have to answer artificial stupidity. But I certainly cannot answer that. And so don't depend on the artificial intelligence to solve all the problems for us. Really need our intelligence to move forward.
Thank you for your insightful comments, Professor Lee. And Professor Aspect,
Yes,
we're also curious about...
Well, first, you should ask experts in artificial intelligence, and I am not one, okay? But I see it as a new tool, a fantastic tool, a powerful tool, but after all, I belong to a generation, and you belong to that generation. When we started to work, there was not computers for solving all these problems. You know, nowadays, the people, they have a problem, they put it on a computer, and they do a simulation on the computer, etc. When we were young, this did not exist, okay? When I was a student, the most powerful computer, mainframe in France, took 24 hours just to calculate one Fourier transform, okay? 24 hours to calculate one Fourier transform. Nowadays, you have your smartphone, boom, you have a Fourier transform. And there are plenty of examples. So the computer has totally changed the way we think about the problems, okay? In my opinion, artificial intelligence is another big step. Is probably a step as important as the one that we had by having computers, but I may be wrong, but up to this point, I don't see that it is different in nature. It's just a new tool. It's so different that we have to learn how to benefit from it. But until the moment when artificial intelligence is able to provide a new physics law, for instance, Maxwell's equation, Schrödinger equation, then if artificial intelligence is able to, by observing various phenomena, to derive a new fundamental law, then I will admit that I am wrong. Until this point, I think that it is a tool, a fantastic tool, you must use it, it's very useful, but it is a tool. And we have to be intelligent enough to use that tool.
Thank you. Thank you both for your insightful comments on how you see AIs. Professor Lee, would you like to add something?
Well, Dr. Aspect was talking about we didn't have computers. When I was a student doing X-ray crystallography, doing Fourier transformation of the machine and crank the number and crank the machine, you do the number. So at the end of my research, I have very strong arms. and that was what is missing now. We really crank the calculator backward, forward, and backward. And, it's a different time.
Yeah, thank you for sharing this.
I can add something. Before computer, people had to be smart. I mean, let's take trying to calculate the exact trajectory of planets. It was the case in 19th century. They have developed all sorts of approximations that we still use nowadays, called perturbation theory, secular approximation, etc. All these methods were invented by astronomers who tried to calculate the exact trajectory taking into account the fact that you have another planet here, another planet there, etc. These approximation methods are still extremely useful because the difference between straightforward computer calculation and doing calculation based on this approximation is that with approximation you have an idea of how the result evolve as a function of this parameter or that parameter. When you do brute force calculation, you have a result. The result is correct, but you say, oh, now if I change this parameter, what happens? And then you have to do a new calculation. While if you do a calculation based on perturbation, you say, oh, if I change that parameter, this is how it will change the result. So, of course, we must use computer, okay? There is no doubt. But we should not forget about all these smart methods of approximation which were invented by physicists and mathematicians at the time where there was no choice. Either you are smart or you don't do anything.
Yeah, thank you both for sharing your insights. I think it is still important that we have to use human intelligence and our insights to guide those tools so that we will be really heading towards artificial intelligence instead of artificial stupidity. Thank you. Okay, so let us now begin the third question. So we're going to focus on interdisciplinary collaboration and innovation. So collaborative efforts across multiple disciplines is now becoming a key factor in addressing complex challenges. So we're wondering, given your extensive experience, so how collaborative efforts contributed to major breakthroughs in your own research? And what strategies would you recommend for young students or next generation scientists when they would like to take a multidisciplinary approach? So Professor Lee, I think, would you like to start by sharing your thoughts?
Well, discipline is something that the older generation decided, physics, chemistry, biology. But when you try to solve a problem, then you have to learn some of the engineering problem and physics problem, chemistry problem, and then there's no discipline. So when I received the Nobel Prize, somebody said, you're a physicist, you're not a chemist. But when you learn, you have to learn chemistry or chemical structures and reaction, you have to know fundamental law of physics. So I did spend lots of time learning physics. And my daughter was interested. She graduated from the Department of Sociology at Berkeley. Then in sociology, she has to collect lots of data, and pretty soon she became a data scientist. Now she's a professor in the College of Engineering at the University of Washington. She's an engineering professor, but she got a degree in sociology. There's no any discipline you have to learn across all the different fields. So I think it's wrong for some of you young people sitting here and said, I'm a physicist, I'm a chemist, I'm a biologist. And there's nothing like discipline. You have to learn it all. When I design a machine, I'm really like an engineer. Even one screw holes, how precisely we have to be located, how deep you have to drill, and all these dimensions has to be decided. So you say I'm an engineer. I'm a tennis player.
Yeah. Thank you, Professor Lee, for sharing your thoughts. Professor Aspect?
Well, I have some kind of opinion, which is that all this politics, which tells us you have to be interdisciplinary, is not efficient. What is efficient is that each of us starts from a field. First, you should have one field where you are very good. Because if you are not very good in one field, you are superficial everywhere. And then it's up to you to find that starting from your field, you can do something interesting with other people. But in my opinion, it's really the freedom of research, of basic research, that at one point you decide that there is something interesting to go. I have some of my former students, they start with laser cooling of atoms, and at one moment they become interested in biology and they go to biophysics. It's wonderful. But nobody told them, oh, you have to go to biology. It's different. They discover that there are problems that they can approach with their method of physicists, and progressively they learn biology and they do it. And in my opinion, that's the right way of doing it. At the end, you should be aware that in physics, there are really two totally different branches of physics. One is called condensed matter. It's about solid, liquid, and stuff like that. And another branch, which is dilute matter, that is to say, atoms separated from each other with interaction at a distance and stuff like that. And optics, photon is also dilute matter in a sense, and with strong separation. But by the end of my career, it turned out that some problems of condensed matter could be addressed with the method of cold atoms. And it was very interesting and I learned some condensed matter. But once again, it was because suddenly it was clear that some problems of the other people could be addressed with my method, so I started learning them. I did not decide one day, oh, I want to learn condensed matter because I want to do interdisciplinary. In my opinion, it's not the way it works. It works in science. Very important thing is meeting people. And you meet somebody who works in a field different from yours, you start talking, and then at one moment you say, well, we may have something interesting to do together. And then you begin to be interdisciplinary. But the big programs where they tell you you have to be interdisciplinary, okay, politics people like to do that. Sorry, Mr. Minister. But he is not of that kind. You are professor, you are not minister. So he has, it's just like wave particle duality. He is both minister and professor.
Thank you both for just really enlightening conversation. I think the message that I receive is that we should just follow our passion and do the things that we do and to the best, and without predetermining which field or define which field we are in, and also keep an open-minded. We be open-minded and talk to people, and with that, those different perspectives will just come in naturally. Right? So thank you for your insights again. So let's turn to the final pre-collected questions before we move on to the Q&A. So for the last question, we would like to turn our attention to how research reaches beyond the lab by connecting with society. So as leaders in both science and society, we would like to see how you view the role of scientists in communicating their research to the public, and also, importantly, how do you balance advancing your research with addressing its broader societal impact? Professor Aspect, would you like to begin by sharing your thoughts? Or I think this may be something that may keep some moments of thinking.
Well, I can tell you, you had an example in my conference. I try to communicate my passion. It's important. And I try to show that applications of science can be useful for society. And what else can I do? And well, one thing we should do is to explain people that things are not magic. Even phenomena which are very, very surprising, there is a rational way of understanding them. We must use a rational approach. For instance, when there was this COVID, okay? If you want to know if a vaccine is good or not, you have to rely on real statistics. Not say, oh, this one is good, the other one is not good because this country has done it, or that country, or that professor, or another professor. You make a rational evaluation of the vaccine, and then at the end you conclude. And it's scientific method. So what we must communicate to the public is a trust in the scientific method, in the fact that the scientific method is extremely robust. What I mean is that sometimes we have examples of some wrong discovery. And what I call the robustness of the scientific method is the fact that very rapidly it is settled. The debate is settled. I can give you 2 examples. In the 80s, there were people in university, Mormon University in the United States. They claim that they have observed nuclear fusion in a chemistry experiment. Okay. Well, why not? After all, you could have lowering the Coulomb barrier and favoring things. Why not? As soon as they released the preprint, it was already clear that it was not usual standard research. And you know, publication is very important. You can judge the quality of a research by the publication. Probably everywhere in the world, but I can tell you what happened in France. In France, we had a meeting of all the physics groups of our department, various groups. And we say, who among us could do a test of what they claim? We found that there was a group in nuclear physics that could do a test. They started the test, and in less than 2 weeks, they discovered that the results reported by these people was nothing else than the traces of radioactivity still surviving in the atmosphere from the test of the American in the Bikini Islands of the 50s. The people could identify that in the Nuclear Institute in Orsay, okay? And very rapidly it was clear that he was wrong. Almost at the same time, a few years difference, there was a claim of observing high temperature supraconductivity. It was just as surprising. There were demonstrations that it cannot exist. Demonstration, between quotes. But you know, the wisdom was it cannot exist. But some people come and say, look, we have a superconductivity at a higher than usual temperature. It's still cold, but higher than usual. Immediately, several labs started. And after a few months, it was clear that it was a true discovery. This is the scientific method, okay? This is what we have to explain to the society, that the scientific method is robust. When there is a surprising results, people do not say it's impossible. People would say, let us try to reproduce it. If we reproduce it, it's a real phenomenon. If we don't reproduce it, it's just fantasy. I'm using a polite word.
You're talking about spending time communicating your science or doing your scientific research. Actually, when I took my first postdoc, I worked with Professor Mahan. Very wonderful thing he did to me was that, Yuan, you want to work with me as a postdoc, it's fine. I have lots of money. You do whatever you want. And I want to take sabbatical. He went, he left. So as a postdoc, the first postdoc, without a boss, without somebody tell you what to do, what you not do, and I have all the freedom to build some ion molecular apparatus. And that was a very wonderful time. My second postdoc worked with Dr. Hirschman at Harvard University. Again, he told me the same thing. When you came here, you will have to go beyond the alkali age. And then he took sabbatical. He went to Germany. So I took 2 sabbatical without my boss. And that's the wonderful thing. The best thing in my life, that you have freedom to pursue what you want, and nobody tell you what to do. So when I start with my student, I refrain myself to tell what to do and do whatever you want to do. But I have limited amount of money, not like Professor Risva or then Bruce Bain. So it's a wonderful experience. Don't work for somebody who's too bossy, tell you what to do. Work for somebody, tell you, do whatever you want.
Thank you for sharing your experience and for emphasizing the importance of science communication in building trust and also delivering the scientific methods to the public.
Yeah.
So, it's time that we move forward for live questions. And due to the time limitation, I would just take one or two quick questions from the audience. So the floor is now open for questions. So if you have a question for either of our laureates, please raise your hand and a staff member will bring you a microphone.
Hello, Professor Aspect and Professor Lee. You have both dedicated many years to planning and conducting your own experiment. Did you ever consider abandoning this line of research? What motivates you to persist? Thank you.
Thank you for your thoughtful question. So I think the question is about like how you proceed through some frustration and challenges. Will Professor Aspect would like to begin?
Yeah. Okay, main motivation is curiosity. Okay, I had the opportunity to settle a debate between Einstein and Bohr. This is a big goal, okay? The best, or among the best scientists in 20th century, they had a debate. I can do an experiment to settle. This is fantastic. But in the everyday research, it's not like that. In the everyday research, I'm sure you had the same experience, you have a leak in your vacuum chamber. And you must find where the leak comes from. And you have to fix it. And this is extremely interesting because it's just like a police, search. Where is the culprit? Is it that gasket? Is it another one? And you have to be smart to find why you have a leak and why the pressure is not as low as you were hoping. So in the everyday development of the method of experimental physics, it's extremely interesting. But the general goal is curiosity. You want to bring an answer to some fundamental question. But you don't all the time think to that question. You think about your leak or about your lasers that does not work. Why does not this laser work? You have to find out and fix it. That's the beauty of experimental physics. I'm pretty sure he has the same experience. Leaks in vacuum chambers, right?
Actually, what motivated me is that many people believe that it is impossible. When I was designing the apparatus, Professor from Caltech will go through and said, Yuan, it is not possible. And that's something motivated me. I said, I want to prove that I can make it possible.
I fully agree. When somebody tells you it's not possible, you want to show it.
That's right. And my wife did learn a very good lesson. She want my help to working with my kid. When she said it is not possible, then I'll come running and come to help. Otherwise, I will not come.
Thank you both for reminding us that it's important to keep curious, and also that motivates oneself is to prove the possibility of impossibility. Right. Okay. For the last question, today we're fortunate to have students from France joining us today. So I would like to know any questions from French students. It can be French, and I believe that Professor Aspect will kindly translate that for us.
Where are they?
En français ou
En français. Allez, ça va donner un peu de peps.
Vous pensez qu'il peut avoir une troisième révolution quantique, par exemple liée à la quantisation de la gravité? Est-ce qu'il y a quelque chose encore qui est encore possible à chercher au-delà des deux révolutions quantiques?
Ok. Now, the question is about the third quantum revolution, which happened if we can quantize gravitation, or the general relativity. That's a good question, and it's wishful thinking. I mean, we don't know, but we can hope that it will happen. And the comment that I can make, which is there is somebody who is extremely active in that, is Roger Penrose. Okay, he's a theorist who got the Nobel Prize a couple of years ago, an expert in general relativity and an expert in quantum physics. Okay, and sometimes he hypothesizes that when you quantize gravitation, when you quantize something, there is always some kind of fundamental fluctuations. And so he makes the hypothesis that maybe these fluctuations are the reason for a fundamental decoherence of big objects. Because there is a fundamental problem that we don't really understand in quantum physics. Why is it that we don't see quantum phenomena at the macroscopic scale? Why is it that we don't see the Schrödinger cat both dead and alive? It's a fact that quantum phenomena, you see them at the microscopic level, individual quantum object. Let's say 1,000 quantum object, but not 1 billion of billion. And 1 billion of billion is macroscopic, okay? This is and so there is some hypothesis that when people succeed in quantizing gravitation, maybe there are fluctuations, okay, fundamental quantum fluctuation, which are responsible for decoherence. But once again, it's wishful thinking. But wishful thinking is useful because people can think of it and maybe one day somebody does that. Anyway, at that time, to my knowledge, we don't have any indication that this will be successful, but it's good to dream. When people try to entangle more and more qubits to build a quantum computer with error correction code, at some point they may find this barrier between the classical world and the quantum world. This is one of the reasons why it is so interesting. Of course, research with quantum computers is interesting because if we can build a quantum computer, it's fantastic. But if we find a barrier, it's also very interesting from a fundamental point of view.
Yeah, thank you for sharing your excitement about the unknown future ahead. But due to the time limitation, we have to close the question now. But before we conclude this forum, I would like to ask each laureate to share a brief message of encouragement for students here. They are passionate about pursuing science. So Professor Lee, would you like to start with your advice for students?
I said, don't believe nothing is impossible in this world, and just believe that you can make it possible. And so I want our young students to be able to solve all the problems. And don't let problems solve you.
Thank you, Professor Lee. So, Professor Aspect, what guidance would you offer?
Well, in a sense, it's similar. Don't think that it's impossible to solve the problems that we are facing. The problems that the planet is facing, that we are facing because of the planet, are very serious, but science is an approach, and you have to learn science, and if you are strongly committed to solving some problems of the planet, use the science you learn to make efforts to solve these problems. And in a sense, don't think that it is impossible. Don't think that solving the problem of too much CO2 in the atmosphere is impossible to solve. There are several possibilities to act on it, okay, and study science in order to be able to attack this kind of problems, okay? And when I speak of science, I speak in a broad sense, okay, including at some point sociology. For instance, if you want to convince people to behave in a way which is less producing less CO2, you just not only tell them you should do less. You have to understand sociology. And so, but don't just think that you can speak like that without any rational basis. Sociology is also rational. So basic science, mathematics, physics, chemistry, biology, and also sociology in a sense, learn any of these and apply it to solve the problems of the planet. It is your planet, no longer ours, okay? No, it's true.
I want to challenge Dr. Alain Aspect. We'd like you to come back again and don't say it's impossible.
Thank you.
Thank you both for those inspiring words. Like, we have to study science to solve the problems and make impossibility possible. So I'm sure that you'll resonate with many future scientists in the audience today. So it has been a great privilege to engage in these insightful conversations with our two laureates, Professor Aspect and Professor Lee. So I hope that this discussions is going to excite new ideas and curiosity. And I'd like to thank also to the audience for your considerate questions and active participations. Thank you all once again.